Good to go. All right, ladies and gentlemen, welcome back. I'm still playing with technology here, trying to get things organized such that I know how it works. So please bear with me as we mess around. I'm also waiting on a few things to come in. So it's coming along. With regards to the lab, I sent an email to you last night, and I will have more information this afternoon. I am going to keep everybody as informed as I possibly can. I understand that it is frustrating for everybody, myself included. So, like I said, I'll keep everybody informed. I am recording this class. I'm not recording it through Teams. I'm recording it on my end. And so I will be uploading these to YouTube shortly, basically after class. I generally upload just one of the videos because they're basically me repeating myself, and we'll go from there. So yes, so these videos are available. I know some people have experienced problems, but a lot of people are saying that the video is coming through crystal clear. I am at the university, so I have the highest bandwidth transmission possible. And so somewhere along the line, one student did comment that getting a TELUS booster seemed to help them get a higher quality signal into their homes. I was asked to just put in a plug for the environmental science students. I guess their association is the League of Environmental Science Students. And I guess outside of COVID, they have social events. I'm hoping they don't have social events now. I'm not even going to inquire with them about it. I trust them. So if you are interested in environmental science or the environment in general, please consider associating yourself with this group. It's nice to have a group of like-minded people that can to have conversations with and get to know, and potentially have different activities as they have on this slide. So if this is of interest to you, please consider contacting them and joining them. We are going to start Module 1 today. Module 1 is on chemical kinetics. And just as an overview, we are going to be looking at both thermodynamics and kinetics in this course. Thermodynamics investigates the direction and extent of a chemical reaction. And if you look at the figure, it is the difference in energy between the reactants and products in this figure. Whereas kinetics investigates the rate of a chemical reaction. And here it is the difference in energy between the reactants and the top of the barrier. And that's what we're going to be looking at throughout this module. Looking at kinetics, discussing that profile, and being able to not only understand but predict chemical reactions from the perspective of chemical kinetics. So these are the units, sections that we're going to be looking at. Basically, we're going to be looking through all of Chapter 20. Section 2010 is presented in very detail in the textbook. I'm not going to be presenting it in that much detail. It will be to the level that I present herein. Basically, we're not going to be doing any of the math associated with what's in Section 20-10. Excuse me. At this point in time, you should have skimmed through all of Chapter 20. That is, just kind of looked through it, looked at the pictures, read a little bit, to try to understand. I'm not expecting you to understand the material, but I want you to know what we're going to be getting to as we go through the next week and a half of course. And skimmed the entire chapter and then read the first few sections. We will be finishing off, or getting close to finishing off, 23 today and 25 or 6 on Friday. So we're going to be moving through this material fairly quickly. There's going to be more examples as we get to the end of it, which of course takes up more time, but it's the stuff at the end that's, I guess, the new material, the more interesting and engaging material. So, as I mentioned, kinetics is the study of the rate of chemical reactions. So, chemical reactions occur on vastly different timescales. They can be very fast. They can be combustion reactions, or faster than that would be explosions. On the other extreme is slow chemical reactions, like the oxidation of iron or the conversion of biological matter to oil and coal. The fossil fuels that we have, well, were based on life, matter that was living tens and hundreds of millions of years ago, gotten into the ground, and while it didn't take hundreds of millions of years for the reaction to convert it to coal and oil, it did take tens of thousands of years, and then it's just kind of been sitting there ever since. In between the extremely fast and the extremely slow reactions are neutralization reactions, biological processes, things like cooking, are things that happen on an everyday time scale, few milliseconds to a few hours, chemical reactions. Collisions between the entities, between the reactants, is required. If you have reactant 1, reactant 2, they need to collide so that you can break chemical bonds and form new chemical bonds. So that is an absolute requirement of chemical reactions. There are several factors that affect the rate of a given reaction. The first one is concentration. If I need these things to collide, if I have more of them around, i.e. a higher concentration, then they're going to collide more frequently and you're going to have a faster rate of reaction. The state of matter also matters. Sorry, that wasn't meant to be a joke. The state of matter is also important. Gases and liquids mix at the molecular level. They literally get together and intersperse, and so you have much more contact between reactants in a gas or liquid mixture, whereas if you have a solid, it only can react on the surface. The bulk of the solid behind it doesn't react. It can't be exposed to reaction. Like, say, if we're oxidizing iron, only the surface rusts and falls away, exposing more metal. Temperature affects the rate of reaction. If we increase the temperature, we increase the amount of energy that's available, and just going back to this figure right here, we get more energy to go over top that barrier. The more energy we have, the more molecules can overcome that barrier and react to form products. And finally, we have the presence of a catalyst. A catalyst actually lowers that barrier, which ultimately increases the reaction rate. All right. It's just going to take me a second to get all of this organized. We are going to do a demonstration, and I need to move a few things around. Like I said, I haven't got everything completely organized here in terms of the technology, so please forgive me as I put a lab coat and safety glasses on. No comments on the safety glasses, please. All right, we'll go with this first. What we have over on the left-hand side, that's a cylinder of gas. It's a metal cylinder. I have just the cap here, and I don't know if it's easy to see, but inside of the cap, there is rust that is forming on the surface there. This cap's probably been around for 15, 20 years, and it is slowly oxidizing. This is steel wool. Okay, this you can buy in a hardware store, and it is used for very, very fine sanding of wood to remove actually sandpaper marks. And it is very, very finely divided iron and comes apart like this. So the surface area on the steel wool is much greater than it is in the cap. So if you have one of these and you use it, if woodworking has been something that you've done in the past, or if you have metal scrubbers for cleaning, you'll know that once you get them wet and you use them, within a day or two, they're very, very rusted. So these things are going to rust much faster than this at room temperature, just simply because of the increased surface area, increased contact between the oxygen and the steel wool. Just going to put that down right there. So now I've got the steel wool right there. And of course, have matches with me, or else I would be able to use a match to light the steel wool. So I figured I would do what you see in demos and possibly see it on YouTube and see if I can start this using electricity. And so simply by, there we go. Simply by current, that current was enough to, with resistance, to cause the steel wool to actually glow. It is actually burning, so increasing the temperature has increased the reaction rate. Now, how about concentration? I've looked at the surface area is greater, heat has increased the rate. How about we now add oxygen? Oxygen is the other reaction here. So this is just an oxygen source. And you can see when I add oxygen, I'm causing this reaction to go significantly faster. And if anyone asks, the burn marks on the floor were there already. What's left, and I don't know if you can see it, but right now it's giving off a lot of heat, and it is actually glowing, and it's slowly fading away. The reaction of iron with oxygen is a very exothermic reaction, so while some of it has reacted to produce rust, the rest of it has ultimately formed molten iron, and that is what is present, remains there, is molten globules of iron. If you were in class, I'd be able to, in a few minutes, pass that around so you can see it, but we work with what we've got. Sweet. Does anyone have any questions on that? We're good? All right. So let's look at the rate of reaction. And we define the chemical reaction rate, which is a measure of the change in concentration with the change in time of an entity. There we go. So the rate of a reaction, given the symbol V, is the change in concentration over the change in time. If we look at the figure that we have there, that figure is of the hydrogen-oxygen reaction, another demo that I might do, only because it goes boom. And here we're starting off with equal amounts of hydrogen and oxygen. So the relative concentration on the left-hand side is 1 for each of hydrogen and oxygen. But because the stoichiometry is 2 hydrogens plus oxygen, hydrogen is used up 2 times faster than oxygen is depleted. And so when all of the hydrogen is gone, you're still left with some oxygen in this reaction. So the change in concentration is presented there as delta O2 and delta H2. Because of the stoichiometry, delta H2 is twice the change in oxygen concentration. Similarly, we have the water growing in, because this reaction is occurring at elevated temperature, it's a combustion, you produce gaseous water, and it grows in comparable to the hydrogen as it depletes because of the stoichiometric coefficient, and you could also measure the change in concentration of hydrogen. Something that you should note here is that if I monitor change in concentration for oxygen and hydrogen, I actually get a negative number. It's, for example, where those arrows are at, it's around 0.6 is the final, 1 is the initial. That means my change in concentration is negative, and that introduces a problem. The rate of change of hydrogen and oxygen and water differ in both magnitude. Hydrogen is used up twice as fast as oxygen, and water is produced 2 times faster than oxygen. And the sign, it's negative for reactants, it's positive for products. We ultimately want a rate equation that gives the same rate and a positive rate independent of whatever entity we are monitoring. And I'm just going to give you that rate equation, and then we'll explain it. So I've taken that change in concentration over change in time, and I've added two parameters. I've added a plus minus to make it positive or negative, and I've added the 1 over x term in front. This course doesn't require calculus, but calculus and kinetics are quite linked, so if you do choose to take this in future courses, you will be looking at it from a calculus perspective. I just want to point out for the students that are in calculus, that do have the background, that this expression, change in concentration over change in time, at the limit becomes the instantaneous rate dx dt. Okay. I'll be doing that a number of times throughout the course just to point out that it exists, but we're not going to be doing any calculus in this course. So what about this term, this new rate equation? That 1 over x term is a way of normalizing the rate as a function of stoichiometric coefficient, where x is the stoichiometric, small x is the stoichiometric coefficient. And that plus or minus is a negative sign that is introduced to make introduced for reactants to make the overall rate positive. So if x is a reactant, we put a negative sign in. If x is a product, we use a positive sign to make the overall rate of reaction positive. In addition, I can take that rate equation and I can rewrite it ever so slightly. And I'm rewriting it in the form delta x over delta t is plus or minus x times v, the rate. That's something we're going to see in a little bit, and it is called the differential rate equation. It's just one form of that rate equation. But when we look at determining the reaction orders in a few days, we will be using the differential rate equations as a starting point for that. And if you're taking calculus, that's dx dt. So let's start with an example. We want to write the rate equations for the general chemical equation A moles of A plus B moles of B reacts to form C moles of C plus D moles of D. So just for convenience, I'm going to rewrite that. And now we want to write the rate equation. So the rate here is equal to, because we're working with reactants, it's a negative sign, negative 1 over the stoichiometric coefficient A, change in A, should be an A, over the change in time. That is how we would write the rate equation with respect to reactant A. We could do the exact same thing for B, negative 1 over B, change in B over change in time. For the products, we have a positive sign, 1 over C, change in C over change in time. And we can do the same thing for D. So that is how one would write the rate equation for any of the reactants or products in that chemical equation. All right, I would like you to write the rate equations for the hydrogen-oxygen reaction. So apply what I just did to the generic reaction, A plus B goes to C plus D. Go back in your notes to look at the hydrogen-oxygen reaction and write the rate equation for that hydrogen-oxygen reaction? Go for it. I'll call you back in about 10, 15 seconds. What you should have written down is this: -1/2 change in hydrogen over change in time, negative O2, change in O2 over change in time, or 1/2 change in water over the change in time. That is the rate expression for the different reactants and products in that hydrogen-oxygen reaction. The next question is more of a thought experiment. I want you to think about it and answer the question: does the reaction stoichiometry affect the reaction rate? And I've given two examples here. 2H2 plus O2 reacts to form 2H2O, or dividing through by 2, we have hydrogen plus 1/2 O2 reacts to form H2O. So take 10, 15, 20 seconds right now, and then type your answer into the chat, please. Yes or no, does the reaction stoichiometry affect the reaction rate? Anyone want to offer their thoughts on this? Yes or no? Got a whole bunch of no's. Oh, by the way, it's cheating if you scroll to the very top of this chat window and see what everyone else answered. And we have a lot of people saying no. No one's willing to jump on the yes bandwagon. So I'm not one for joining, but I would argue that you are all correct. Someone pointed up earlier that the ratios are the same, and that's one way of looking at it, yes. Another way that we can look at this is to just think about what we've done here. To go from the first reaction to the second reaction, I just divided through by 2. Some people prefer the first reaction because it doesn't have fractions in it. Some people prefer the second reaction because it keeps the largest stoichiometric coefficient at 1. So it doesn't matter how you write it, it's the same reaction. The molecules don't know what you've written down. You could have doubled it and gone 4, 2, and 4. The molecules know that when they react, there's a probability that they lead to product formation. So no, the reaction stoichiometry does not affect the reaction rate simply because it doesn't know what you have written down. It shouldn't affect it. The reaction is going to occur no matter what, whether you're monitoring it or not. So good deduction on your part to figure out that the answer to that was no. So now we want to look at measuring reaction rates, okay? Chemistry is a science. We want to study something. We need to know that a reaction is occurring. What ways can you conceptualize for determining if a reaction is occurring? I've got 4 broad classifications that we're going to get to, but right now, what can you brainstorm for? How would you know a reaction's occurring? How would you know the reaction's occurring? Go for it. Chat, or you're allowed to talk. Yeah, but how do you know the product's forming? Physical changes. What do you mean by physical changes? Heat, yes. If a reaction is getting warmer or colder, there is a change in temperature. That you can tell as the reaction's occurring. If there are bubbles, bubbles is a gas-forming reaction. Yeah, so if you see bubbles, a precipitate would be a solid-forming reaction. So yes, excellent there. Changes in color has gotten out there. Changes in appearance. appearance could be a precipitate forming, settling out, changes in color, all of these things. So yes, you've got these. If we want to categorize what you are presenting, these are the 4 categories. Okay, we can monitor a reaction spectroscopically. We can look for changes in color. That's in the visible spectrum, but we have instruments in the laboratory that can look outside the visible spectrum into the infrared, into the radio wave. A lot of instruments measure spectroscopically. We can look at them electrochemically, where we can measure a voltage or current. And we have pH probe is one classic example where you have it's an electrochemical cell. That's another thing that we're going to be looking at this term at the end of this course, is looking at electrochemistry, and looking at how a pH probe works is one of the things we're going to talk about. A lot of people mention thermally. We can look for temperature changes. Is the reactant getting hotter or getting colder? And if we specifically design a system that is controlled, we can actually get quantitative data over how hot or how cold something gets. You did a calorimetry lab last term, virtually, unfortunately, but you did a calorimetry experiment, and that's exactly what you were doing. And chemically, we can look for changes in, if gas bubbles are given off, we can monitor gas pressure. We can look for mass of a precipitate if a precipitate is forming, and that type of idea. So chemical processes as well. All right, so those are the ways we can look at a reaction. What do we want to get quantitative information, and that quantitative information, we're going to first look at something called the reaction order. I've already given one expression for rate, as in change in concentration over change in time. Here's another expression for rate, and it deals with the fact that for a reaction to occur, the reactant entities have to collide. And so if we change the reagent concentration, there are going to be more reactants present, more possible collisions, and with more collisions, the rate at which products are forming is going to increase. That gives us this equation here, whereas the rate is some rate constant K times the concentration of the reactants, A and B, raised to, and for now it's arbitrary coefficient, M and N. Also, the products can be included in here, raised to, again, coefficients P and Q. What are these terms? K is the reaction rate constant. It is a parameter that determines how fast the reaction goes. It gives us information on that barrier height and a few other things. We'll be looking at that in a couple of days. So K is the reaction rate constant. M, N, P, and Q are the reagent reaction orders. So A is raised to M, B to N, and so on. And those are the reaction orders with respect to A and B and C and D. They typically range from -2 to +2, and they're typically integer or half integer values. So that is M, N, P, and Q. The total reaction order is the sum of the reagent orders. So in order to calculate the total reaction order, we simply sum up M plus N plus P plus Q, and we get the total reaction order. And we can assign names to that as well. If the order is 0, it's a 0th order reaction, 1 is a 1st order reaction, 2 is a 2nd order reaction, and 3 is a 3rd order reaction. So, okay, and we'll be spending more time looking at the rate constant in a little bit. What we're going to do now for the next couple of classes is we're going to look at reaction orders and different ways of determining the reaction order. We're going to spend a little bit of time looking at dimensionality. The reaction rate from change in concentration over change in time, delta concentration over change in time, has the units moles per liter second. What I want to look at is the dimensionality of the rate constant K for 0, 1st, and 2nd order reactions. What is the units on the rate constant? So first, I'm going to simplify this expression just a little bit. and we have V, oops, wrong color. V is equal to K, and I'm just going to make it simple, a to the 0. And we can have V is equal to K, a to the 1, first order reaction, and V is equal to K, a to the 2. That's a second order reaction. If you are typing a comment, I can't actually see it in the screen. So yeah, you'd have to speak it out, or someone could speak it out on your behalf. Okay, I'll go look at it. No, the slides don't go in and out of focus. It's your connection, unfortunately. So a couple people had that problem in the other thing. If it does, I'd have to look at it, but here, I'm just going to make a note to look at it at this point in time when I'm looking at KA0. It shouldn't, because it's getting a feed from my tablet, and that doesn't have a camera associated with it. So, okay, back to this. This is a 0th order reaction, 1st order reaction, and 2nd order reaction. For all of them, the rate has the units of change in concentration over change in time, or moles per liter second, is equal to K times moles per liter raised to the 0th power. Now, what is anything raised to the 0th power? I got the answer on the chat, because I can flip over here. This is equal to 1. It is always equal to 1. So that means that the units of K are moles per liter times second. That is the units of K for a 0th order reaction. If we apply the same thing to a 1st order reaction, we have moles per liter times second is equal to K times moles per liter, now raised to the 1st power. Well, moles per liter cancels with moles per liter, and this produces K is equal to units of 1 over seconds. I would like you to do this for the 2nd order reaction. And it's probably going to be, well, chat or voice. Do that, and then tell me what units you get for the units of K, please. Anyone have an answer? I have Bailey saying it's liters per mole second. Benjamin, I think, seconding Bailey's response. I'll go with that. Yes, it is liters per mole seconds. And since Bailey wrote it that way, I just want to touch on something. If you put liters per mole seconds, that's actually ambiguous. Can I write more clearly the equations? It's a little hard to read. I will try. I'm getting used to writing on a tablet. This could mean liters per mole times seconds, or S, or it could mean liters per mole seconds. So this is ambiguous. In order to make it not ambiguous, if you want to write it on a line, you just simply need to put brackets around it as I had done right here. Liters per mole second. And that clarifies that it is all in the denominator. Good. Second example we have on this page is, I'm telling you this, the rate constant is that. It's a constant at a fixed temperature. Talk about that in a couple days. We want to derive the combined rate equation for this. Now, in last term, you derived the combined gas equation, P1V1 over N1T1 equals P2V2 over N2T2. What did you do there in terms of deriving that combined gas equation? Anyone? You are allowed to talk. I'm not monopolizing the talk thing here. How did you derive the combined gas equation? What variable, what value is missing in that combined gas equation? R. So in determining the combined gas equation, you set R1 equal R2. Well, that's what we're going to do here. So we have, I'm just going to rewrite that equation. V is equal to K like that, and K is a constant. So we are going to set K1 equal to K2. So the steps that we're going to do, first thing we're going to do is solve for K, and then 2, equate K1 equal K2. And the solving for K, I'm going to actually do on the fly. So if I want to solve for K, I'm just going to put it in green. K is equal to V1 over that. The reason I put all the ones in there is because K is also going to be equal to V2 over A2 to the M that, and that's 2. I can rearrange this and get V1 over V2 is that expression right there. So can I have someone remind me if I have a to the power of x over b to the power of x, how can I simplify that expression? I'll wait. A to the x over b to the x simplifies 2. Yep, several people have responded with this simplifying to simply a over b all to the x. And I'm just going to apply that here, and I end up with the expression v1 over v2 is a If I do it for all of them, I get that. And what I have just written is the combined rate equation. And like the combined gas equation, this is the combined rate equation, where I can now compare two different runs of the same reaction, which is what we're going to do right now. Does anyone have any questions on this derivation before I continue? All right, so if we look at that expression again, we have collisions between reactants are required for the reaction to occur. That should be intuitively obvious. The reactants need to collide to break bonds, form bonds. But is it reasonable that the product concentration affects the reaction rate? And the next bit was supposed to be hidden. It's not. I'll fix that. No. Only intuitively, you only need reactants coming together for a reaction to occur. The products are ultimately become the spectators watching the reaction occur. However, sometimes we do see a dependence on the product concentration. And what this means is that you've got a complex system. The complex system could be an equilibria that we're going to be looking at in a little bit, or it could be as complicated as what's occurring inside of your body with biological feedback. So your body self-regulates with a negative feedback loop, if you're taking biology, where if you produce too much of something, other mechanisms step in to reduce them down. So there's a very complex biological feedback process occurring within your body where the products, C and D, definitely affect the rate of that reaction. So if you do see a dependence on the product concentration, it means you've got a complex system occurring. What we want to do is try to avoid equilibria, avoid the complex system. So we are going to use the method of initial rates. And your first experiment, whenever Hayden McNeil gets it fixed, uses the method of initial rates. So in this method, the reaction rate is measured a short time after the reactants are mixed. So, and additionally, you measure it for a very short period of time, such that only a small amount of product has formed or a small amount of reactant has actually reacted away. So the method is ultimately convenient because the initial reactant concentrations are known and stable. You have a container filled with A, a container filled with B. They're not doing anything right now. Then you mix them together, and then the reaction occurs. So time zero is fairly easy to determine. Bing, reaction starts. There is a minimal of entities. You have the reactants A and B. So the number of products is zero, and ultimately we're going to make it such that the product concentration is constant, but you minimize reactions that are occurring at the same time, called concurrent reactions, and reactions that occur consecutively. All of that is minimized using the initial rates method. And then we determine the reaction order by measuring the rate while varying the reactant concentrations. So we're going to do the exact same thing again and again and again, but just change the concentration of reactants, and what comes out of it is a way of determining the reaction order. We'll look at an example in 2 slides. But one thing I said in the previous one is that we're going to make it such that we don't have to worry about the products. And so how are we doing that? We use or design a chemical reaction such that the same amount of product is produced in each experiment. So you're always producing the same amount of C and D in the reaction, and then once you got that, that means that the ratio of C1 over C2 and D1 over D2 is always 1, and so those two parameters leave, ratios leave, and you're left with an expression that depends only on the reactant concentrations. So we get the order of reaction is dependent on A and B, the reactants alone. So here's the example we're going to look at. We want to determine the overall reaction order and the rate constant for the reaction of nitrogen monoxide with oxygen. And we run this reaction to produce the same amount of nitrogen dioxide in each run. When you do the lab, you'll realize that the reaction produces the same amount of iodine in each run. That's how it's timed. So in this case, we're producing the same amount of nitrogen dioxide. Here is the chemical reaction, 2NO plus O2 reacts to form 2NO2. And then there's the data that we collected. Excuse me. So just to give you a little bit of background on this chemical reaction itself, the nitrogen monoxide plus oxygen reaction is actually one of a major ozone depletion reaction. And if you lived in a big city or visited Los Angeles or Vancouver, Colorado even sometimes, Denver, Colorado even sometimes, you see a brown haze that hangs in the air. It's generally most visible in the morning and the evening. That brown haze is actually nitrogen dioxide. It's a toxic, well, oxygen's the only non-toxic gas in that list, actually. So, all right, so let us go through and do this. Okay. So for this reaction, and I'm just going to write it out, we end up with V1 over V2 is equal to that expression right there. Excuse me. And as was noted, we run the system such that NO2 1 is always equal to NO2 2, which means this always simplifies to 1. So what we're left with is an expression using right there. So we can now go back and look and try to figure out which reactions we are going to use. I still have two unknowns, the nitrogen monoxide and the oxygen concentration, but if you look at runs 1 and 2, they actually have the same oxygen concentration. That is actually by design as well, because it allows us to cancel out oxygen, and so what ends up happening is we have rate using runs 1 and 2, you end up with the rate for reaction 1 is 0.043 moles per liter second. The rate for reaction 2 is 0.280. And that is equal to 0.015 moles per liter over 0.038 moles per liter raised to the power of m, and 0.027 and as I pointed out before, there's 0.027 because the number is the same. This becomes 1. If you do the math, what you're left with is 0.154 is equal to, oh, should also point out that the units all completely cancel. 0.154 is equal to 0.395 raised to the m. Someone want to help me? How do you determine m? And where am I in teams? All right, I'm back. I love technology. All right, I'm back. I love technology. Sorry about that. Oh, for frick's sake.
I think you've been muted.
Not only have I been muted, I was kicked out of Teams. So my link to the Teams thing disappeared. We should be back to normal. I think I just got kicked out, right?
Yeah, that sounds right. It just paused
Yeah.
Just paused and couldn't do anything.
I love technology. Honestly, I do. All right. How do I go? What I was asking here is, how do I go about and calculating m for this reaction? Has anyone put it in the chat yet? Using method of logs, yes. So going over here, if we apply logs to all of this, we end up with log 0.154 is equal to m log 0.395. I will let you do the math and confirm, but we go through and solve this, we find out that m is 2.01. We're not done yet because m, the order needs to be integer or half integer. The order is integer or half integer. So clearly this makes m is equal to 2, and the reaction is second order in NO. Second order in nitrogen monoxide. Given the time, we are at a point where the class is over. When we come back on Friday, I will continue working through this example with method of initial rates, and we will definitely be getting into integrated rate expressions, which I think is sections 20-5 and 4 and 6. So that's where you should be in your reading for Friday's class. With regards to the problem set, you don't have enough right now to start the problem set, but by this weekend you definitely will have enough information to work on the problem set. Does anyone have any questions? Oh, one of the things posted is, how do we find these videos on YouTube? There is a link now to a channel in YouTube. That link is in Blackboard, and you can go on there, and this video will be uploaded in just a few minutes. So in the next half hour, it will be up on Blackboard. Look under the course resources section in Blackboard. When will it be posted? Next half hour or so. When will the lab start week? Will the lab start next week? I have no idea. If I can get it working today, I would like to get them started today because our subscription is limited. But what it comes down to is I really don't know how and when Hayden McNeil is going to get this thing fixed. So I will keep you informed. I sent you an email last night. That's the latest information I have from Hayden McNeil. I gave them a whole bunch of email addresses to upload, and that's where we're at. So I will keep you informed. But if I can get it operational today, I would like to have the labs, we start this lab this week. And I'll give you longer to do the experiment. I won't cut it off on Thursday. Are there other questions? All right, if there are no other questions, everyone have a great couple of days and expect to see some emails from me with regards to the lab. Everyone take care. Bye now.